Okay, so we will start this session. I am Julio Chaname. I will be chairing this session. And we will be starting with Magdalena Vilaxa campus, talking to us about the impact of binary mass transfer in the Accretor's measurable parameters. So, Magdalena.
Okay, hi everyone. My name is Magdalena Vilaxa Campos. I'm a second-year master's student at Universidad de Concepción, and I'll be presenting an update on my current master's thesis project. It's an update, so none of this is final, but it's titled Understanding the Impact of Binary Mass Transfer in the Accretor's Measurable Parameters. So first, I guess many of you may know, since this is a blog called about binaries, but binaries are nothing out of the common for stars overall. About 30% of sun-like stars are actually part of binary systems, and more than 10% are actually part of higher-order systems. So understanding binary evolution is actually very crucial to understanding serial evolution overall. So in 1981, Paget estimated that only about 10% of a star's initial mass should be accreted by the star in order to reach critical velocity. This will mean that most mass transfer products will be actually rapid rotators. However, rapid rotators prefer low-dense environments, as found by Ferraro this year. And what's special about low-density environments is the fact that since there's a lower chance for dynamical interactions, there's a higher chance of survival for wider binary systems. So overall, the properties that a star gains or changes due to mass gain are very poorly understood. This can be seen as color, brightness, rotation, or even abundances. So our main goal for this project is to characterize the change in observational properties on a repeating star due to mass transfers, depending on the original parameters of the system. This is the system we'll be working with. This is what we will usually see for a binary star. These stars are close to equal mass, but the blue stars that here is our donor, pink is our accretor, but the donor is slightly more massive and has evolved beyond the main sequence, therefore becoming bigger. But if we were to look at this system as a point particle representation and fix on our accretor, we'll get something like this, where our accretor is fixed in place and the donor is orbiting around it. This new orbit, as the solid black line, has an eccentricity and a semi-major axis shield labeled as A. And the dotted line is the orbit of the L1 point. This is the point where the gravitational potential of both stars equate. So what we're going to do is we take this L1 orbit and we let go of a single parcel of mass. You can think of it as a small packet or a single particle, and it will fall onto the accreting star following a ballistic motion. We will repeat this. You will see in a later plot, but that's the main idea we're working with here. So the general assumptions to do this experiment are as follows. First, the effect of the donor's potential in an infallible parcel of mass will be negligible. Then, the effect of a stream can be described by the superposition of all of these single parcels. The radial component of the velocity at the moment of impact with the accretor will contribute to the thermal energy of the accretor. And impact will be defined as when the distance from the parcel to the center of mass of the accretor equals the radius of the accretor itself. And the tangential component will contribute to the rotational energy of the accreting star. Now we have to limit our free parameters. First, for the orbital separation, if we even want a star to start losing mass, now whether that mass is accreted by the accretor or not is a whole other story, but if we want this blue star to lose mass, its radius has to be larger than the radius of its Roche lobe. So taking Eggleton's approximation, we get a restriction. Then, for the initial velocity of this parcel, if we were to trace the movement of a particle in the surface of a star that is non-rotating, the velocity it has will be too big to ensure we get direct impact from that parcel into the accretor. So an additional velocity countering the orbital motion should be added in order to ensure this happens. We took the limit to where here, the blue line, which is the trajectory of the parcel. This is very exaggerated. It's a very big accretor and a very small orbit. But the limit is when this touches the surface of the star at least once. Knowing that limit and knowing the orbital velocity of the system, we can constrain the additional velocity that will be given at the surface of the donor. This additional velocity can either be a representation of the rotation of the donor, or it can also account for random motion of the particles in the outermost layers. So both of these limitations that I just showed were tested on a circular orbit, which is not very realistic for what we're working with. We'll be working with a whole range of eccentricities. So for an elliptical orbit, where all points in the orbit are not at the same distance from the center, we'll be taking, for simplicity, velocity at periapsis, since it's the point where the orbit is the fastest, therefore we get a final range of velocities that is bigger to work with, and separation limit at apoapsis. Since at that point, the radius of the Roche lobe is the largest. Now the experiment. This is the step-by-step of what we did here. Given both masses for the binary system, A, E, and V extra, an orbit is defined, as we saw previously. Then, at each position of the orbit, the velocity and its angle with respect to the radial position define a new orbit for the infalling parcel. The semi-major axis and eccentricity for this new orbit are stored, and a flag indicates us if an impact, direct impact to the accretor occurred for that specific orbit. This is repeated for a wide range of V extra, A, and E. We end up with something like this. This is point at time 0. This, once again, is the orbit of the L1 point, and this parcel will follow this trajectory, the solid line. The dotted line is just the rest of the orbit for completeness, but that won't really occur since we will stop everything at this point. And if we repeat this over time, we'll get something like this. This is just a couple of orbits that I selected to show. The only difference here from the previous plot is that these red orbits are the ones that completely miss the accretor and therefore didn't impact directly. If we were to see this over time, we'll get something like this, where each parcel has its own orbit. And I repeat this for a single period of the binary. So what do we find from here? The plots I will show, this and a couple more, are the radial in red and the tangential in green components of the impact velocity average over a single period. So we see here that clearly the tangential component dominates throughout the whole domain of V extra that we tested. And we also see clearly that there's a peak close to this orange line. And what's curious about this is that this orange line is actually the value of the orbital motion of the donor around the accretor at periapsis. What we get from here is that we get the maximum contribution to the rotation of the accretor for velocities similar to the orbit itself, or we can also say that the spin up is maximized for systems that are close to being tidally locked. If we were to think about this V extra as the rotation of the donor, we know that donors should rotate very slowly since they expand and there's a conservation of angular momentum. So if we were to restrict this to very low values, our maximum will be given for points where the orbital motion is the slowest. This will be achieved by having wider orbits or less eccentric orbits. This is consistent with the fact that we see most rapid rotators in low density systems. Now for the same major axis, we get this, once again, the tangential component dominates throughout the whole domain. And don't worry about the spikiness here at the beginning. It's mostly a resolution issue. It takes a while to compute the distance to the L1 points across the whole orbit, so I didn't really get time to take more measurements. But I have seen this being solved with just more measurements. For the eccentricity, we get pretty much the same. But since we are taking the limit of the velocity based on the periapsis, it's highly dependent of both A and E. So I think that we will still need further research mixing values of B and A and B and E to better constrain these two parameters, eccentricity and semi-major axis. And that's pretty much everything. Thank you.
Thank you very much, Magdalena. Thank you also for being fast enough. Questions for Magdalena, please. Questions? So I'll start maybe with one that is, I have a wonder about since I studied this in class. It's not working? Can we turn it on? Or maybe there. So,
Hi, yeah.
So this should be, I guess, simple. But your first depiction, right, of the Roche lobes. So I have always wondered if that shape is always very close to circular of the Roche of the lobes.
No, not really.
And how the fact that you define a radius, which is defined for a circle, right, would affect anything.
Yeah, okay, so the Roche lobe is actually more of a tear shape, a teardrop shape. But there's here by Eggleton, there's also a previous approximation that approximates the volume that this lobe should have to that of a sphere. So that's a radius that is measured. This can also be like, if we didn't get the results that we were expecting, I can also change that distance from the approximation given by Eggleton to my separation minus the distance to L1 point. So that can also be made.
Okay. So, but is it hard to try to model it with its actual shape?
Yes, it is.
Is it sometimes very different than a circle?
Yes, because the shape, even if it's always a tear, it changes depending on how far the stars are apart. So it's not consistent overall.
Right. Thank you. Questions, comments? Okay, so over here.
There.
So the material that misses the star, wouldn't that form a disk and eventually fall anyways?
Yes. This, let me go to the one with the red. There. All of the orbits that do not impact the star directly don't necessarily are lost. Since we saw like in this, that some of them might be very close together. If they were to impact each other, we could actually get an accretion disk. But for this experiment in particular, we were focusing purely on the direct stream approach. So these were discarded, but it doesn't mean that they would get just lost.
Thank you. We have time for one more question, maybe, or comment. Doesn't seem to be the case. So Magdalena, thank you very much.
Thank you.
Our next speaker, I have to wait a little second. Okay, excellent. Maite Echeveste is going to tell us about Blue Stragglers in Collinder 261. Thank you, Maite.
Gracias. Bueno, buenas tardes, buenos días. Bueno, primero quería agradecer a la organización por permitirme dar esta charla. Yo soy Maite Echeveste, soy estudiante de doctorado de la Facultad de Ciencias Astronómicas y Geofísicas de La Plata. Me dirige Omar Benvenuto y Alejandra De Vito. Y hoy quería traerles algunos resultados de un proyecto en el que empecé a trabajar este año. El proyecto está enfocado en las estrellas rezagadas azules, las Blue Stragglers, y lo hacemos también en colaboración con Giovanni Carraro, que está en Padova, en la Universidad de Padova, en Italia, y María José Rey, que trabaja para la ESO en Chile, que la van a escuchar en un ratito. El proyecto tiene una parte observacional y una parte teórica. María José y Giovanni son los que se encargan de la parte observacional, y nosotros desde La Plata, junto con Jorge Paney, hacemos los modelados teóricos. Entonces, me imagino que muchos ya saben, pero para repasar, las estrellas rezagadas azules son estrellas que se encuentran en diversos sistemas estelares. En particular, en los cúmulos se las puede localizar en una región del diagrama color-magnitud que está por encima y a la izquierda del punto de Chernoff, o sea, son más luminosas y más azules que el punto de Chernoff. Acá les muestro dos ejemplos. Uno es M3, que es un cúmulo globular. Esta imagen es muy famosa. Las estrellas serían este conjunto de por acá. Y el de la derecha es un cúmulo abierto, King 2, donde las Blue Stragglers están marcadas en puntos azules. Como pueden ver, están como si fuesen una extensión de la secuencia principal, pero lo que pasa es que si uno piensa en la evolución estándar de estelar de estrellas aisladas, estas estrellas no tendrían que estar ahí porque ya deberían haber evolucionado. Entonces lo que se cree es que son estrellas que adquirieron masa en algún momento posterior a sus inicios. ¿Cómo adquirieron esa materia? Bueno, depende del entorno principalmente, ¿no? En cúmulos abiertos, que es el caso de Collinder 261, el canal favorito para la formación de estas estrellas es mediante sistemas binarios con transferencia de masa. También pueden acretar material si colisionan entre sí, entonces se fusionan y crean una estrella más masiva. Y obviamente pueden pasar las dos cosas en simultáneo. Entonces, ¿qué es lo que nosotros queremos ver en este proyecto? Bueno, vamos a estudiar el canal binario, que consta de dos estrellas de secuencia principal. No son idénticas, por lo tanto, una es un poquito más masiva que la otra, y es la primera que evoluciona, la primera que llena su lóbulo de Roget, y transfiere material a la estrella, a su compañera, a través del punto de Lagrange L1. Bueno, recién estuvieron hablando de eso, y en la charla de hoy a la mañana también. Eso es un escenario que se llama binarias interactuantes, donde la transferencia de masa se da por desbordamiento del lóbulo de Roget. Entonces, nosotros queremos ver si ese mecanismo puede dar cuenta de la existencia y de las propiedades de las Blue Stragglers de corto periodo que están en Collinder 261. ¿Cómo vamos a hacer eso? Bueno, vamos a usar un código numérico que se desarrolló en la facultad, principalmente por mis directores, y vamos a estudiar el espacio de parámetros iniciales del problema, que también, como se nombró hoy a la mañana, es bastante grande, porque son justamente dos estrellas. Vamos a estudiar las masas iniciales de esas dos estrellas, el periodo orbital inicial y la eficiencia en la transferencia de masa. Que también, justamente, hoy a la mañana me vino muy bien esta charla. La mujer que dio la charla nombró que eso era uno de los puntos claves en la evolución de binarias interactuantes por transferencia del lóbulo de Roget, ¿no? Saber cuánta de ese material efectivamente es acretado por la estrella receptora. Vamos a ver si las simulaciones alcanzan la zona del diagrama color-magnitud donde están las Blue Stragglers a la misma edad que la determinada para el cúmulo. Esto parecería, no sé, bastante inocente, algo fácil de hacer, pero la realidad es que hay que ajustar bastante los parámetros porque lo que no queremos que suceda es que los sistemas evolucionen demasiado o sean muy jóvenes, digamos. La mayoría de los sistemas que nosotros evolucionamos, lo que pasa es que cuando la estrella accretora recibe suficiente material, también llena su lóbulo de Roget. Entonces la binaria entra en contacto y se crea una especie de envoltura común que hace que las estrellas empiecen a orbitar cada vez más cerca, en una especie de espiraleado, y se fusionen. Eso también es un mecanismo para la formación de Blue Stragglers, pero no serían progenitores para nuestras Blue Stragglers, porque en nuestro caso son binarias donde hay un periodo orbital observado, entonces no pueden ser objetos que estén fusionados. Así que no creemos que el sistema llegue a la edad de Collinder 21 en esa situación. Tampoco queremos que sea demasiado joven como para que todavía no haya transferencia de masa. ¿Sí? O sea, tenemos que buscar la edad justa. Bueno, acá algunos resultados. Esto es un diagrama color magnitud. Los puntos azules son las observaciones. Es un diagrama donde hay varias curvas. Todas tienen la misma masa y el mismo periodo inicial que está acá arriba. Esto es 0.80 días y las masas iniciales de las dos estrellas. Y lo que hace que haya varias curvas es justamente ese beta, que es lo que yo nombré antes, que es la eficiencia en la transferencia de masa. Si beta es igual a 1, toda la masa que sale de la estrella donante es acretada por la receptora, y si beta es menor que 1, hay parte de esa materia que se pierde del sistema. Como pueden ver, para beta igual a 1 es la curva marrón, que está por acá arriba. Bueno, las cruces negras son el momento en que la simulación llega a la edad del cúmulo. Pueden ver que a medida que beta es más chico, se va barriendo el diagrama color magnitud hacia zonas más débiles. Y de hecho hay algunas curvas, estas dos en particular, la verde y la naranja, que llegan a la observación en el momento indicado. Son muy buenos modelos. Acá hay otros ejemplos donde las masas son las mismas, lo que cambia de panel a panel es el periodo orbital inicial. Y también pueden ver que sigue pasando lo mismo, que para betas más grandes se llega a zonas del diagrama color magnitud más brillantes, y a medida que beta disminuye, vamos barriendo toda la región donde están las Blue Stragglers hacia abajo. Bueno, como decía en la diapositiva anterior, lo que termina siendo es que beta es un parámetro de importancia clave para poder reproducir las Blue Stragglers más débiles. Bueno, acá hay un conjunto de simulaciones. Esto, un poco a modo de ejemplo, no son todas las que hicimos muchas más. Para que se den una idea, cada una tarda un día aproximadamente, hicimos más de 50 simulaciones. Y estas son variando las masas y los periodos, y de vuelta cada gráfico con un valor de beta diferente. Siempre pasa lo mismo, que se logra barrer el diagrama color magnitud variando la eficiencia en la transferencia de masa. Pero como pueden ver, se alcanza bien en la zona a la edad del cúmulo. Hasta ahora les mostré coincidencias en el diagrama color magnitud a la edad del cúmulo, pero todavía no hablé del periodo orbital. Como mencioné, estas Blue Stragglers tienen un periodo orbital medido, que está acá en la columna derecha. Estas son las mismas que estaban antes, pero ahora en vez de ser todas azules, tienen un degradé de colores hacia el verde, indicando que el periodo aumenta. Y en estos gráficos se puede ver una selección de sistemas que cumplen dos características. Por un lado, cumplen que pasan cerca de al menos una observación a la edad del cúmulo, y que tienen un periodo orbital, también a la edad del cúmulo, muy parecido a esa observación cercana. Cuando digo muy parecido, me refiero a menor que 0.02 días en la diferencia, ¿no? Así que son muy buenos progenitores. Bueno, como conclusiones, esto creo que es lo más importante, un hallazgo de este trabajo, que la transferencia de masa conservativa no puede explicar todas las estrellas rezagadas azules de Collinder 261, al menos con estos periodos. Es necesario que se pierda algo de material del sistema para poder llegar a los sistemas más débiles. Por otro lado, si vemos la big picture de los sistemas simulados de su periodo orbital, está en el rango de las observaciones. Ahora, si queremos ver que se cumplan los 4 parámetros observables que estamos utilizando, la posición del diagrama color magnitud, la edad y el periodo orbital, y queremos encontrar una simulación que ajuste perfectamente esos 4 valores, habría que hacer más simulaciones, que es algo que tenemos pensado hacer. Y algo que también quería mencionar es que tal vez no todos estos sistemas sean producto de la evolución binaria. Podría llegar a pasar que algunos simplemente vengan de otro canal de formación. O sea, también es un poco por ahí ambicioso suponer que todas estas Blue Stragglers van a poder ajustarse a los modelos, eso tal vez no vaya a suceder. Y eso es todo. Gracias.
Excelente, gracias Maite. ¿Preguntas, comentarios para Maite? Por favor.
Bueno, muchas gracias, Maite. Realmente muy linda tu charla, me resultó muy clara. Dos preguntas. La primera es que siempre me deja muy impresionado cuando ustedes muestran este tipo de trabajos, es cómo logran, digamos así, encontrar los parámetros iniciales para llegar a esa zona del diagrama, ¿no? Es decir, si simplemente hacen un barrido general aleatorio o si hay alguna receta, digamos, ¿no?
Sí.
Esa es una. Y la segunda es si encontraron finalmente algún valor de beta preferido, digamos, o un rango de valores de beta preferidos para este tipo de sistemas.
Gracias, Gabriel. Respecto a la primera pregunta, bueno, yo dije que eran parámetros libres, ¿no? Las masas y el periodo orbital inicial. Es verdad, son parámetros libres, pero están acotados. Primero porque para este cúmulo, el punto de Chernoff tiene una masa medida, es de 1.1. O sea que las estrellas no deberían alejarse tanto de ese valor. De hecho, la estrella, la secundaria, que es la originalmente menos masiva, debería ser menos masiva que eso. Y con el periodo orbital pasa un poco lo mismo porque queremos llegar a periodos orbitales chicos, y si uno parte de un periodo orbital muy grande, lo que pasa es que los sistemas divergen y terminan con un periodo mayor al inicial. Y después yo tenía la suerte de que ya había algunas simulaciones hechas, porque esto es un trabajo que se empezó a hacer el año pasado, creo. Entonces me podía ya dar una idea de más o menos los valores que tenía que empezar a probar. Igual probé un montón de sistemas antes de llegar, sobre todo esto que nombraba de la edad, porque por ahí sí llegaba a que las curvas pasen por esa zona, pero o eran muy viejos o muy jóvenes. Me costó más ajustar la edad. Y bueno, el beta fue medio una corazonada que, no sé, tuve, porque ninguno de beta igual a 1 era imposible llegar a esa zona. Y ahí dije, bueno, capaz que si se pierde materia, bueno, alcanzan luminosidades más altas, ¿no? Más débiles. Y ahí se empezó a barrer. Pero es medio artesanal, digamos. Y respecto a qué regula beta, ¿no? No sabemos. Como pasa, yo vengo también de estudiar otro tipo de sistemas, estos que emiten rayos X y tienen un objeto compacto, pasa lo mismo. En la literatura se suele asumir que algunos trabajos dicen que es igual a 1, otros ponen 0.5 como un valor intermedio, pero no hay ningún mecanismo físico en el modelo que regule ese valor. Es desconocido. En el caso de este trabajo, además, nosotros habíamos pensado que tal vez beta podía estar relacionado con el momento angular de la materia, porque la estrella está rotando y al caer en la otra estrella viene con momento angular, así que tal vez se pueda llegar a formar alguna especie de disco, pero tampoco hay observados para estas estrellas. Entonces también, si pensamos así, beta tendría que estar relacionado con el periodo orbital, y pareciera que no, según esto, porque como ven, el periodo orbital está muy desordenado. No hay un orden aparente de las Blue Stragglers en cuanto a su periodo orbital. Así que estamos, no sabemos. Igual si alguien tiene alguna idea, bienvenida.
Gracias. Hay otra pregunta por allá. Un segundo, si nos esperas un segundito, por favor.
Hola, muy buena la charla, muchas gracias. Y estaba viendo que el valor 0.65 o el 2 sigma, por así decirlo, que no está, ¿no? Es decir, en el anterior era entre 0.50 y 0.75, en la ficha anterior, acá sería entre 0.47 y 0.71. Me parece que una eficiencia del 60%, no, un beta del 60%, podría llegar a ser el parámetro.
El preferido.
Mi preferido sería probar con en este por aquí, ahí.
Sí, en los intermedios es verdad que, sí, tenés razón, porque de hecho los más bajitos, acá se ven algunos, este de 0.25, o este de por acá, o este de por acá, y acá se ven más. Están demasiado abajo. Y los de beta igual a 1 tampoco ajustaban muy bien. Sí, la verdad que sí, los intermedios eran los mejores, sí. Sí.
Sí, siguiendo un poquito en esa misma línea de estas dos preguntas, a mí se me ocurre que si quisieras constreñir beta, ¿cierto? Yo tomaría, por ejemplo, quizás todos tus resultados que te dan lo que más o menos donde debe caer, pero compararía lo que me llevó a esos resultados con las propiedades de las closed binaries en cúmulos muy jóvenes, las condiciones iniciales, quizás, ¿me explico? Y ahí, porque deben haber condiciones iniciales que no existen, quizás.
Y de hecho este cúmulo es bastante viejo, tiene como 8 gigaños.
Ok, y esa memoria se pierde entonces.
La verdad que
¿Crees?
yo no sé, pero voy a averiguar, es interesante.
Ok. Creo que tenemos que terminar acá. Muchas gracias, Maite.
Bueno, gracias.
Okay, our next speaker is, I'm not going to be able to pronounce your last name correctly, Marco. So this is Marco here from Rio, apparently, the local group Symbiotic System Population. Thank you, Marco.
Okay, so good morning, everyone. I'm Marco Laversveiler, and I'm going to present to you something about my undergraduate work in Valongo Observatory from the Federal University of Rio de Janeiro. This is very hard to use right here. And okay, so what are symbiotic systems to start with? First, they are binary systems, and secondly, they have, of course, two components, a hot one and a cool one. The cool one is mostly evolved giant star, which can be RGB or AGB star. And the hot one, it's mostly, in most cases, white dwarf. And they show also an ionized nebulae, which is very similar to planetary nebulae. And also the main characteristic of these systems is that they are, of course, they are interacting, so they have mass transfer. So this happens mostly by winds, and in some cases can also happen by rush-lobe overflow or by a similar phenomena, which is a wind rush-lobe overflow. Wait, no, here. And okay, so why do I want to know how many symbiotic systems are in the galaxy or in the local group? Well, first because I have to pay my bills, but I also want to know a census. It's good to have a census of the binary and multiple systems in the galaxy, and of course binary evolution channels, and which help us to understand a little bit more of how binaries evolve. Also interaction phenomena, which can be also accretion, jets, outflows, recurrent novae, and so on. And a topic that I'm going to tell you a little bit more at the end of the talk is that they could be related to type 1a supernovae. And okay, my work is divided in 3 steps, and the first one is an empirical derivation of the minimum population expected in the Milky Way. So for this, I use position and velocity data from symbiotics in the galaxy here. And I try to understand the distribution related to the galactic height. This is, I derive a scale height for the systems in the galaxy. And then with help of orbit integration, with collaboration with Jorge Pinto, we separate the systems in components of the galaxy. This is thin disk, thick disk, and halo. And then we integrate the whole population to get the number. So this is a result, a tomb diagram, which shows the velocity space of symbiotics in the galaxy, the ones we have also position and velocity data. And on the right, you can see the selection we made for the systems in the galaxy. Here you can see the orbits. So you can see that symbiotics, of course, in the disk have more circular orbits on the left. And on the right, you can see that symbiotics on the halo, of course, have more chaotic orbits orbits. Okay, so for the results of the first step, we have the number density of symbiotics, which is about this number. And with the integration of the model, we then have a population expected of at least 3,000 to 5,000 symbiotic systems in the galaxy. And also with the classification we made, we can separate something about 45%, 19%, 36%, respectively, for the thin disk, thick disk, and halo symbiotic systems. Okay, for the second part, we have a statistical derivation of the symbiotics in the galaxy. And using some input parameters, which you can see here, and we put some zero-age mid-sequence parameters for the symbiotics, and then we evolve them, statistically evolve them, using some predefined evolutionary channels. But which channels we use? This is an example from these autos here on the bottom. And you can see this one is specifically for symbiotics. But the major picture of the problem is much more complicated. So you can see here a general view of binary evolution. And for my work, I specifically use this part here for symbiotics and low mass stars. And from this, I construct my view of the evolution of binaries to form symbiotics specifically. And the main difference about these channels is that on channel 1, on the left, you can see that there is a Roche lobe overflow during the main sequence phase of the primary star. The second one, you have the Roche lobe overflow for the giant phase of the primary star, which can happen on the RGB or AGB phase. And on the third channel on the right, you can see that there is no Roche lobe overflow during the entire evolution of the primary star, not necessarily the second one. And we then input the parameters, which I showed you before, and then we evolve statistically the systems from the input parameters. And this was, of course, the hardest part of the work, which took a lot of time and also a lot of my hair. These are the results. So for the Milky Way, we have about 40,000 symbiotics, and for the local group dwarf galaxies, you can see that we have something from 1,000 to also 0 symbiotics expected in some of the smallest galaxies of the local group. This shows the same information, but with a plot showing the relation with the visual absolute magnitude of the galaxies, and you can see a most linear relation here in the log space. Okay, but what does the literature tell us about us? Well, you can see that the authors do not agree with each other. So we go from 1,000 to 40,000, 100,000, sorry, symbiotic systems. And with our results, we are something in the middle, which is not a bad thing, but also not necessarily a good thing. But you can see, I don't agree with them also. So that's the thing. And for the final part of my talk, I would like to talk about a little bit the type 1a supernovae from symbiotics progenitors. And for this, we use initial final mass relation, which shows basically the expected mass of the white dwarf with respect of the initial mass of the progenitor star. And for this, we derived something about a 6 solar mass star, at least, to 1.1, at least, white dwarf with classical evolution, stellar evolution. And we also assume that symbiotics have how do I say this, unchanged population in the galaxy. So they form in the same rate as the die. So using this information and this assumption, we can then derive these rates for type 1a supernovae with symbiotics progenitors. And as you can see, for the Milky Way, we have the highest one, and it's already 10 to the minus 4. And if you compare with the expected total rate of type 1a supernovae and in the Milky Way, we can see this is at least 10 times smaller. For the dwarfs of the local group, you can see that the value is even smaller. And for this case here, we don't expect we expect no supernovae 1a from a symbiotic in the entire history of the universe, because the time scale from this rate is greater than the age of the universe. Here's the same information also related to the visual magnitude of the galaxies. And of my conclusions, we can see that I have expected population of the symbiotics in the Milky Way of at least 3,000 to 5,000. An expected population which goes to 10 to the 4th to 40,000 at least. For the dwarfs of the local group, something about 2 to 4 magnitudes smaller. And compare the rate of type 1a supernovae for the galaxy, which we have some numbers, we can see that from symbiotic progenitors, we could expect about 0.5 to 3% of supernova wave from symbiotics. So the major getaway message with this talk is that symbiotic systems, even though they could be progenitors of supernova wave, that absolutely are not the main one progenitors. And this is all. Thank you.
Thank you, Marco. We have plenty of time for questions and comments over here.
Também acepto perguntas em espanhol.
Hey, hi, excellent talk. So you were mentioning that you're giving some parameters before doing the statistical evolution. Which are some examples of those parameters that you give as inputs?
Here. So I have some same major axis and period distribution for these systems. Also, initial mass function, which in this case I use also just from the Crow, and a binary fraction or multiplicity frequency, which shows us how many binaries or multiple systems we have in each galaxy. For the Milky Way specifically, I used a multiplicity frequency, which shows that how many systems are multiple in the Milky Way related to single ones. And with these parameters, then as an input observational parameters, yeah, I then evolve them using my code.
Okay, thank you.
And following that up, what is you think the most impactful in your results?
What do you mean with this?
The one that of those assumptions,
Of the assumptions?
what is the one that impacts the most your results?
Probably, yeah, this one here, which shows us how close the binaries are related to each other and if they are going to interact a lot or
like that,
no
for example, we know that in the galaxy, in the solar neighborhood, the closed binary fraction is a strong function of metallicity.
Yeah.
So is that what, for example, determines the differences between thin disk, halo, thick disks, etc.?
In my case, I used a function as a function of the primary mass, which is in this reference here. So they show the multiplicity frequency for the Milky Way as a function of the primary mass of the system, which is like a step function. It goes up to higher mass stars, but does not has a major impact because we know that higher mass stars are the minority of the stars. So, and the majority of the binary and multiple systems are in these high mass stars, these high mass systems.
But you are accounting for the different metallicity between the environments?
I just account for metallicity when I change the galaxies.
Okay. Right. So that's where you are using it. Okay. Thank you. More comments, questions? Back there are first Francisca, then Thomas.
Hi, thank you very much for your talk. So you showed a table with the galaxies and the amount of symbiotic systems that you would expect. And this is also related to what Julio was asking. So I'm sorry, but for me, it's still not clear why you don't expect any symbiotic systems for Carina, Draco, and Ursa Minor. And how can that actually be related to the metallicities or other parameters? Like, why do you have those results?
Okay, in this case, it's mainly because these galaxies here are very small. So they have they don't have too much stars. And as we see on the evolution channels, symbiotics are not a very easy system to be formed, at least from this reference here. So you don't expect, at least from what I was doing, a high population of symbiotics. So if you have a galaxy which is too small, you probably don't have symbiotics. You don't expect to see symbiotics, but it doesn't necessarily mean that there are not symbiotics, because Draco, for example, Draco has one symbiotic confirmed.
So it's mainly statistics.
Yeah, statistics. We don't expect in majority to see, but you can see 1, 2, 3, but not like 1,000.
Okay, thank you.
Thank you. Thomas, last question.
Last question, last but not least. I'm afraid you will lose more hair
Probably,
on this project, because I think, as Julio correctly pointed out, the size of a star depends on the chemical composition of a star at a given mass, right? And so that, I think, will be the principal component in this game. So you need to take into account the metallicity distribution function of each of those systems.
I use the metallicity, but for example, for one galaxy, I was like the mean metallicity of the galaxy to do the evolution. So when I change the galaxy, I change the metallicity also.
Yeah, but I think within a galaxy, you have a metallicity spread, right? And that will wash out all of your numbers here. Or not wash out,
not
change,
but you change it,
exactly. So I think searching for the principal components is a fundamental ingredient for all these correlation plots that you showed.
Thank you for the suggestion.
Okay, we can agree to that. Thank you, Marco. Great talk. Te quieres escapar. Okay, next speaker, Maria Jose Rain from Chile, working at ISO. So blue and yellow straggler stars in galactic open clusters. Thank you, Maria Jose.
Many thanks for the introduction. I'm afraid that this presentation is a little bit more observational than what we have heard previously. And basically, I'm going to present you what I did during my PhD project. And yeah, I'm an ISO fellow in Chile with duties in Paraná. So before starting, thank you to all my collaborators for their help. And also thank you for the organization for having me here presenting my work. So our understanding of stellar evolution is built upon the synergy between observations and theory. And within this context, open clusters are the closest thing that we have as laboratory for studying stellar evolution. And when positioning the cluster member in a color magnitude diagram like the one I'm showing you here, I don't know how it works this. Oops, I don't know if it's working. Over there. Yeah. It's becoming more and more common that not all the stars fly along the traditional expected path of stellar evolution. This is, for example, the case of M67, where 25% of the evolved stars are classified in alternative pathway stellar products, such as X-ray binaries, blue straggler stars, yellow straggler stars, subgiant stars. So within this context, understanding the formation and the future evolution of these stars is very important. And okay, I think I can safely skip this slide because Maite already covered the properties of blue straggler stars, but I think it's very important to let you know that there are many formation mechanisms that lead to the formation of these objects, from binary evolution to stellar collision, and even dynamical encounters in hierarchical triple system via cosine lead-up mechanisms. So within this context, blue straggler stars are not only important for understanding stellar evolution, as they are also important to understand, for example, mass transfer processes like Rochelle overflow or common envelope evolution, which are also very essential to understand many other systems, such as symbiotic stars, double white dwarf, supernova type 1a, X-ray binaries, etc. So we wanted to understand on which type of cluster blue straggler stars feel more comfortable. But also we wanted to make targeted observation in the multi-wavelength regime. And for that reason, we have searched for the blue and the yellow straggler stars across the galactic disk in open clusters. I have to tell you that there was a previous compilation about this in the literature, but however, with a couple of problems. For example, it was based on highly homogeneous data. This means that the authors have taken different photometry studies from different authors using different techniques. They didn't account for the contamination of field stars, but also the lack of membership information, where only few stars have radial velocities, proper motions, etc. They don't even have reported the position of the stars, making it extremely difficult to work with the data. So in this new compilation, we have addresses all these problems. The data comes from Gaia, so it's a highly homogeneous data. We have accounted for field contamination, but we also provide the membership information. This is the 5 astrometric solution of Gaia, parallaxes, proper motions, colors, magnitudes, etc. The catalog is already available. You can use it, it's public, so yeah. So how we did this catalog, and one by one on each cluster, and by using a very simple tab query, we download the Gaia data, and together with the Python version of UPMAS, we have assigned membership probability to all these stars. And once we identify the members, we have fit, the isochrons, of course, computed with the cluster parameters. Then we added the 0H main sequence and a binary sequence. Both are very helpful when constraining the blue and the yellow straggler region. Particularly the binary sequence is very helpful when constraining this region here, because it's usually populated by normal binary stars. And once we did this, we have isolated the blue and the yellow stragglers candidate, as I'm showing here in the schematic figure. This means that any star falling on these regions has been classified as blue or yellow stragglers. And for that reason, we only call them candidates. So some of the main results here, I'm showing you the combined color magnitude diagram of the nearly 900 blue stragglers candidate we found. The color indicates the cluster age to which they belong. And we found that 27% of the open clusters of this sample host at least one blue straggler, but also that all these candidates start to appear in clusters older than 100 mega years, and that most of them are highly concentrated in clusters older than 2 giga years. While for the yellow stragglers, we found that they are less numerous than the blue ones, with only 77 candidates. 10% of the clusters show at least one of these stragglers, yellow stragglers, sorry. And something that I would like to point out here is that this is the first time that someone is reporting these objects in a catalog. So when comparing the number of stragglers with different cluster parameters, we can provide some hints on the formation mechanisms. And here I'm showing you the comparison between the previous catalog and the new one. As you can see, both distribution are very different. This is the number of straggler versus the age of the cluster. So the previous authors claimed that the number of blue straggler stars increased progressively with age from 3 mega years until 10 giga years, while in our work, we found that this number is almost constant at 0 until 1 giga year, and then it's followed by a step increase towards older ages. For a very small sample of clusters, we computed some fundamental parameters such as the mass and the binary fraction using the code Azteca written by one of my collaborators, Gabriel Perren. And while suspected this relation between these both parameters have never been shown and quantified before, so this is the first time as well that someone is showing it. And as you can see from the plot, the number of Blue Straggler stars on each cluster increase with the increasing binary fraction. There is no correlation with age, and this is, of course, a direct evidence that supports the binary scenario as well. So, changing a little bit the subject, we wanted to explore the mass segregation in these clusters. And since these stars tend to be more massive than normal stars, they tend to sink towards the cluster center as a consequence of dynamical friction. So what I'm showing you here in the figure is the cumulative spatial distribution of the Blue Straggler stars in blue in comparison with that of the reference population, in this case, the RGB. And very generally speaking, we found that in open clusters older than 1 gigayear, Blue Straggler stars are more centrally concentrated. However, this is not so clear like in the case of the globulars. And we also found very weird cases on which Blue Straggler stars are not concentrated at all. We also estimated this parameter here, A, which is basically the difference between the both distribution. So this parameter indicates if the Blue Straggler stars went through mass transfer segregation. I'm really sorry, I'm confused. So the parameter shows the difference between both curves. So this indicates if the cluster went through mass segregation, then the difference between both curves will be higher. This means that we will have a more positive value of the parameter, indicating that the cluster is more dynamically off. So with a list of nearly 1,000 candidates, we follow one of the most natural steps. So we cross-correlated this list with all sky surveys of photometric variables, trying to find interesting cases that can be used for future investigation, but is on the transiting exoplanet satellite survey test, where we did the largest strides and finding these pathological cases. So we download the light curves from the full frame images of tests. We perform a clean and normalization process. This is normal. I don't have much time to go into detail about this. And given the test baseline, we only search for period of between a couple of hours and no more than 13, 14 days. The periods here were derived using the GASP code, which basically use the normal Lom's-Hargel periodogram to derive a periodicity in irregularly sampled data. And once we computed the periods, we computed the phase transit of the binaries, and we found nearly 70 short periods among the blue and the yellow straggler stars. And we also noticed that 90% of these stars are new discoveries. But most interesting is that in 7 clusters of their sample, we found that they have a very high rate of short period between the blue straggler stars, higher than 10%. And this is in striking contrast with what found in the literature, for example, for NGC 188. So these clusters were used in ground-based proposals to perform spectroscopic follow-up, to measure the radial velocities, and to confirm the nature and to confirm also these higher rates. So to go on the same line with Maite talks, I'm going to talk a little bit of Collinder 261. Diving on the ESO archive, we found nearly 700 spectra coming from the low medium resolution spectrograph flames. And we derived the radial velocities. And by using the radial velocity variability technique, we found several binaries in this cluster, long and short periods. We also derived their projected rotational velocity. And as Maite pointed out, there is no relation. They do not follow any logical distribution in the color magnitude diagram. But what is interesting from this cluster is that more than 50% of the population is in binary system. And as you already heard from Maite, yes, we are working on the modeling of especially the short binaries one. So I think I'm going to skip this because I'm running out of time. I would like to promote the studentship at ISO. This is a great opportunity, especially because here the audience is full of students. You can spend between 6 to 2 years in any of the headquarters at Germany or in Chile. In Chile, you can involve with the operations. So it's a great opportunity. Please go through the ISO web page, see if you met the qualifications, and please apply. We are more than happy to receive you there. And I leave you with the main takeaways of my talk. Thank you.
Thank you, Maite. Sorry, thank you,
Maria Jose.
Maria Jose. I saw Maite there. Questions or comments, please. Over there? No, here, down here. Yes.
I was just wondering if you don't mind going back to the correlations. I think you had an age versus number of Blue Stragglers correlation, and then another correlation on the same plot. Yeah, that no, one back. This makes, yeah, just one back, just because you do this normalization. I was just trying to, do you think that the normalization affects the plots in that you're?
Yes, I
as a
think
proxy
it
for
affects.
mass,
Yeah.
you know, affects?
I personally prefer just using the number of Blue Straggler stars instead of normalizing with any reference population. But just I wanted to make the comparison between both studies. Yes.
Okay, thanks.
In the back, please.
Hi, very interesting talk. You've shown a very good correlation between with the age of the clusters, but did you see something regarding the metallicity as well, or not?
No, not really, no. Because at the time we did this work, there was no like an homogeneous catalog of metallicities, so no, we
Okay.
didn't try.
Thank you.
Okay, here, last question.
How complete is your survey? What are the limitations?
Sorry, I don't know if I fully understood your question.
So you've queried the regions around open clusters to look for these Blue Straggler stars. So how complete were you in that respect? I mean, there are constantly new open clusters being.
You mean like outside the clusters as well?
No, well, also outside the clusters, but let's start with the clusters.
I think after we published the catalog, other authors have added more Blue Straggler stars in the new, because with Gaia, new open clusters have been discovered. So I think there are new data as well, but I don't know.
Okay.
I don't know if that answered your question.
Yes, sort of.
Yeah.
Yep, thanks.
Okay, thank you, Maria Jose. And we have a last talk in this session from Alonso Herrera. He will talk about a systematic method to identify runaways from star clusters produced from single binary interactions, M67.
Okay, so good afternoon, everybody. My name is Alonso Herrera. I'm a master's student in the University of Concepcion, and today I will present my research for my master. So first of all, I would like to introduce some relevant concepts that will be mentioned along this presentation. Well, stars that are liberated from a cluster with unusual kinematics are known as runaway stars. They can be produced either by a supernova explosion or the disintegration of a triple system. For this work, we focus on the three-body disintegration that leads to the product to a runaway single and a runaway binary. And our aim is to find observationally the product of this type of interaction. So for that, we use the third data release of Gaia that contains 5D kinematics information for almost 2 billion sources in our galaxy. So we start to define our criteria to identify runaways. And for that, we search for both the single and the binary runaways and the point in the sky where the three stars got separated. And for that, theory predicts that we need a 180 degrees angle between their velocity vectors due to linear momentum conservation. We also assume that the mass of the binary should double the mass of the single, and assuming that the low mass star gets ejected. So we also can assume that the velocity of the single should double the velocity of the binary. And we also want that both sources get to the cross point, the point in the sky where they get separated at the same time. So this quantity should be equal for both. And we also position both sources into a CMD and see if they fall near to the isochron and the cluster members of the host cluster. So this is a diagram for our criteria. We have in here the cross point, the 180 degrees angle that the velocity vector mark, and we have the binary system and the single star in here, and the traceback time that they took to get to the cross point. So we focus on a particular old cluster, M67. Why? Because it's a well-studied cluster. We have a lot of information about M67, and it has a lot of binary stars in it. So how many pairs do we expect to observe in this cluster? Well, for that, we define a field of view with a radius of 150 parsec centered on M67, and the tidal radius of M67 is similar to 17 parsec, and that is less than 150 parsec, that is our field of view. A typical ejection velocity from a three-body encounter is between 1 and 10 kilometers per second, but for M67, we calculate a escape velocity of 2.6 kilometers per second. The travel time for an object moving at 10 kilometers per second to travel the 150 parsec radius is in order of 30 mega years. And the timescale expected for an interaction between a typical binary and any single star is less than 5 mega years. So with that approximation, we get that we are expecting 6 ejected pairs. But can we find these pairs in the Gaia DR3 database? And for that, we did a sample selection. We did a cone search in Gaia that give us around 2 million sources. Then we did a cylindrical cut that is like we're showing here, with 300 parsec of diameter and 300 parsec of depth, and M67 right in the middle of the cylinder. With that, we get 200,000 sources. Then we only use the sources that are escaping the tidal radius of M67 and a velocity of 2.6 kilometers per second. And we end up with 50,000 sources. So we now apply the criteria to all the possible pairs. We did a combination of all the sources, all the remaining sources. So we have the 0 with the 1, the 0 with the 2, and so on. And with that, we come out with close to 120 million combinations for all the pairs. We analyze all these pairs and look the ones that accomplish all of our previous mentioned criteria with 1 sigma. And we quantify now how many pairs each one of our restriction or criteria removes from our sample. So the velocity ratio distribution, if we consider that the velocity ratio is greater than 2, we reduce our sample by 1/2. But if we also consider that the fastest object must be the dimmer than the slow one, this became a reduction of 1 order of magnitude. So we consider from this to here. The traceback time distribution, if we consider that both sources needs to get to the same point at the same time, we reduce our sample by another order of magnitude. And this is our more restrictive criteria, the angle, that if we consider only sources that trace a 180 degrees angle with the velocity vectors, this could reduce our sample by 2 orders of magnitude. And also requiring that the fastest and the dimmest star lies on the isochron to within 1 sigma confidence, we finally further reduce the sample by another 2 orders of magnitude. So we apply all these criteria to all the 120 million pairs that we have, and we reduce the sample by 8 orders of magnitude, and we have 1 pair that survives all of this. So, ta-da! We found something. Yeah, we found something. We have this is our surviving pair that pass all of our criteria. And in the background, we have the cluster members of M67, an isochron fit. And in here, we have our binary star that has a velocity of 28 kilometers per second, and the single one that has 67 kilometers per second. And you can see that the dimmer one is the single star, and the brightest is the binary. So this is the only one that survived, but we predict 6. Where are the other ones? And for that, we did some estimators. We calculate also some false positive. We did a false positive test. So we generate 4 different tests shifting the center of the cluster with different positions. And that in total give us a sample of pairs 5 times greater than the one that we use. So with that, we found 0 objects. So we also consider that how the galactic potential can affect the angle of the sources. And well, the most significant change occurs when the ejected pairs is ejected parallel to the orbital cluster motion, but it doesn't get affected that much when the ejection is perpendicular to it. And well, this is mostly affected for objects that are escaping in small quantities of velocity, but at least for the case that survive, we have that the velocity are greater. So that's it. We found a systematic method to identify runaways from observational data. We took the catalog and we reduced it to 8 orders of magnitude. We use M67 as a benchmark, and only using the 5D kinematics, we obtain some results. And we know that this is our preliminary result, and further observation with the radial velocity needs to be done. And also we can use the metallicity to see the membership of the pairs from the host cluster. And in future work, we want to apply this method to another clusters or larger samples of clusters. So thank you.
Very cool work. Congratulations. Questions, comments? Here in the middle, please, first, and then in the back with Manuel.
Hello, nice work.
Thanks.
I am wondering if you were thinking on applying your systematic search to a known cluster that has runaway stars, observed runaway stars, to see if you get how much you can take with your method.
Yeah, well, we did that with Orion on my first year trying to prove the method. But we didn't have an improved version like I have now for that. And the main focus in my investigation for now was to have the criteria well defined. So I didn't have time to apply to another clusters. And now is the time where I want to do that. So, but that is one of the plans that and the follow-up of or the method to applying to non-runaway stars. Indeed, I get a request that to analyze a cluster, and I want to do it because I want to see the restriction that I have for the criteria. Maybe gas pollution or something like that can affect because this method is sensitive to errors. So yeah, I want to apply it. And if you have something or somebody have like identified runaways, we can try to identify the other pair that gets ejected.
I see.
Yeah.
Can I make another question?
Go ahead.
You mentioned quite low velocity, spatial velocities for the runaway stars. I would expect there to be faster. I wonder if the volume that you consider is limited by these velocities, because maybe they are farther away.
Yeah. That is the field of view. The 150 parsec limits a little bit how many fastest sources that we can find, because they are far away from the host cluster. But for applying to a larger field of view, we also need to improve some coding, because you jump from 120 million pairs to a billion, and that is more difficult. So
I see. Yeah.
But at the beginning of the project, we only used 5 parsecs, and we didn't find anything. Now we found something at 150 parsec, and so we want to extend also the catalog.
I see. Thank you.
Makes sense. Over there in the back, and Manuel. And then we go back here.
Thank you. My question is, if we are trying to apply this method, for example, to globular clusters, we're going to have a larger effect of the gravity of the cluster itself. And I saw you tested the effect of the potential of the galaxy, but how does the potential of the cluster, the self-gravity of it, affect this, particularly this assumption that you have 180 degrees between the ejected and the other pair?
Well, for the first question, what was the first question? I was thinking on the second one.
Like what effect can have the gravity of the cluster itself in the angles that you can get?
Well, at least for the pair that we have, it doesn't affect that much because it has larger values of velocity, but it can be affected if you have that the ejection is parallel to the cluster motion, orbital cluster motion. But if you have it like they get ejected perpendicular to it, they detach from the gravity. So, and also that we have to consider that the sources that I have as a result are the ones that are outside the tidal radius. So they don't have the presence of the gravitational influence of the cluster. So
that's why it's dominated by the galactic potential, right?
Yeah.
Great, thank you.
Excellent. There's a question here.
Thank you, very nice talk. Oh, I will move just. Thank you, very nice talk. But my question is in fact related to the last one. So, because to me it's kind of crazy that you can in some way trace back the kinematics of those objects. So the doubt I had was connected to that one, because I was wondering how can you keep kinematical information of this object? So to what concerns the global potential of the cluster, you already answered. But then I think what happens if you can have other close encounters, especially if the cluster have a low number of objects, it should be highly collisional. And the second effect that I was wondering is So you have a list of criterias, and then so technically, if one look at those criterias and ask himself how likely it is that some field star falls into those criteria, I suppose it's not very likely. But then you said, well, we just found one couple. So technically it will be in accordance to that, but maybe it's connected to the test hypothesis that you did. And so I was wondering a bit about all those things, like how can we be certain that all those criteria that technically they work when we think about the binary system as an isolated system? How good is that assumption here?
Okay, well, for the first question, collisions, well, at least for M67, it's not a dense cluster. It was. So, well, for me, it's still difficult to imagine the dimensions of the space. So I cannot give you like a good answer of how frequently can be the collisions of the sources. But I think that with follow-ups, observation, metallicities that can be affected with the collisions, we can further consider that. I think that the most problematic thing can be the radial velocity more than the collisions, because, well, we don't have good values for radial velocities. At least for the sources that I am interested to see, because there are radial velocity for the cluster members, but I am looking for the one that are outside of them. So I'm more worried on that than the collisions that can be happen. But with the spectroscopic, I think that we can resolve that. And the other question was, can you give me a summary of the other question?
It was about like, how can you be certain, at least without the metallicity, that this is not a field star that just falls into the criteria?
Well, we are not sure about that. At least we are seeing the CMD, and we can say, well, it falls very good to the
Yes,
CMD.
If this is within the main sequence, then I think metallicity will be key here.
Yeah, I think so. Yeah, but we can also not cut the field stars, because we can be cutting a possible result. So that is the tricky part of the method. Well, and I see a poster outside that talks about how to erase field of view of cluster members, but I haven't found the person that have that poster. So please, I need to talk with you. But yeah.
Thank you very much. Very nice talk.
I think we need to stop here. Yeah, we're past. Thank you, Alonso. That was great.
Yeah.